All right. I should
Was
be recording.
okay. I'm gonna imagine there are more people in here. That's what my goal. So welcome to the Project 2 guide, everyone. In this can you like this I guess it's yeah, Nathan, Thomas, yeah. We're tutors for the tutoring center and we will be going over Project 2. Okay. So we'll discuss an outline for each task and section. So there's a total of 6 tasks. We'll give an overview of what it's asking for, and we'll also give resources and content. For example, like we'll guide you to specific pages of the implementation guide if we find those useful. We'll also give out tips and tricks for implementation, and also we'll give our own rating. For context, Thomas and I did this project uh, we were originally with Bozzy and we did this project like 2 years ago. So
Yeah.
we've done this project before. We understand its struggles. So we can hopefully relate our experience and maybe make your lives a bit easier, you know? So, okay, next slide. Okay. And important thing we want to stress is that these slides, this whole recording is not a replacement for the documentation. This is not a replacement for the specifications. We just want to stress that out. This is more of a supplement and more of a helper in case you are confused on some stuff. You should read through the specifications yourself. You should read through each task, and you should be able to understand the pseudocode before implementation. Okay.
All right. So we're gonna do some kind of cleanup work first. Similar to the previous project, you're gonna have to make a parser, preferably a recursive descent parser. Obviously, this grammar is significantly less thorough than the Project 1 grammar. But we still heavily recommend a recursive descent parser because the reason we do recursive descent parsers is because if you follow the formula, it will always be 100% right and it will always pass every test case. Um, Important to remember, epsilon is not a token. So if a rule can generate epsilon, that doesn't mean that epsilon will be returned from something like peak. So like over here, if I'm ID list, and this color is kind of gross, I followed this path, so I'm this rule. I don't get epsilon as a token in return. If we kind of follow the path, ID list is called by right-hand side. It could be an or, it could be a star. That's what would actually be returned by peak. And so epsilons do not actually figure into what is returned. And so you have to kind of grapple with that in this case. It wasn't true of project one. And then syntax errors. Really important to note, the syntax error message is different than the previous project. This is important. Copy and paste this exact syntax error message. Many times students will say, I don't know why I'm failing test cases, and it's because um, they accidentally are missing an exclamation point or something. So just be careful about that. All right. So, important parsing note. Absolutely in no scenario should you start programming any part of the project until you're done with the parser and you've submitted it to Gradescope and you've gotten 100%. Exceptions would be if the Gradescope wasn't up, but I believe it is. And the reason for this is the parser is all or nothing. And if you don't get it right, it's a 15% deduction. And further, if it's not right, you can run into instances where your parser is failing, later test cases that are unrelated, and you have no idea what's wrong. Further, it's way harder to fix your parser when you're done with the whole project and you're going back and you're having to ask, okay, did my new code break this or did my parser break this? So really make sure I would obviously you want to understand the whole project before you start optimally, although almost nobody does that. But you really want to complete your parser before even thinking about moving on. And that means it should just every function should return void and there should either be an output of syntax error or nothing. Um, Storing rules. So this project, as opposed to the other one, leaves a lot of the structure work to you guys. So determining what structures you're going to want to store data in. Before it was given to you explicitly almost, although some were kind of hidden. This time it's kind of up to you, although there's some suggested ones. So we have a struct and it has two fields. We have the right-hand side and the left-hand side. The left-hand side, it's a non-terminal, so it can only be one thing. So it's just a string. And the right-hand side would be any number of either terminals or non-terminals. Um, we want to store those rules in a data structure that's accessible. You can either return the data structures, although you'd have to return it a lot, or you can store it in a kind of global to your parser. And this is covered more extensively in page 18 of the implementation guide, which is really helpful. Finally, we have this interesting case where we do cover epsilon rules here, and it's just important to note that if you see something that looks like this, or a goes to lowercase a, or and then the star, and there's nothing here, these two represent epsilon rules. So if you ever see just a rule with nothing in it, that's an epsilon rule. It's just important to keep in mind that that is a possibility. All right.
My turn. So we're going to start with task one, which is pretty simple. We're just printing out the terminals and non-terminals. I think the important thing to note is that the order of the terminals and non-terminals you're printing is based on how they appear in the grammar. So left to right, top down. So you can see in the example below that the highlights that the terminals and the non-terminals are based on how they appear in the grammar first. Important to note, the non-terminals will obviously be the left-hand side, while the terminals will be what's not on the left-hand side, right? The right-hand side can contain both terminals and non-terminals. Uh, you can move on to the next slide. Sorry. Yeah, like I said before, so for the data structures, it's really up to you how you want to do it. Vectors and sets could be useful. The most important thing is you need to keep track of the terminal, like keep track of the order of the terminals and non-terminals in in the grammar. So I'd recommend perhaps a vector and just inserting each ID into a vector in a greedy fashion. You could possibly also do I don't think sets would work in this case because they would be lexicographically ordered. So I don't think sets would be useful in that regard. But the data structures are up to you, and it shouldn't be too difficult if you plan ahead. And once again, I recommend page 18 of the implementation guide. And we have our own recommendation, or more of our own rating system. The professor wanted us to give context on how long each section would take, but we obviously, the time is very subjective between person to person. So we couldn't really, so we decided more of a difficulty rating system. And we gave this kind of a 1 out of 5 star. This is more so relative to later tasks, specifically tasks 5 and 6, which are way more difficult in this part, I will say. And we want to emphasize the fact that do not get discouraged if this task is more difficult than it may appear, or you're running into issues or taking longer than expected. Each person has their own experience, and basically, it's fine if it's taking longer than expected. Stupid stuff comes up in code all the time, even in the most easiest of sections. So don't freak out if you're like looking at task one and you're like, this is taking way too long for a task one, and the tasks later are way harder. Don't stress out. Each person, has their own way of doing things. Okay.
All right. So task two is to calculate the set of knowable non-terminals. And this is an important one to cover for you guys. This is not necessarily a very complex operation, but from my understanding of your guys' class, you guys put epsilon in first. And in an effort to simplify things, a few years ago, Bozzi created this new kind of set, which is we call knowable. So in Bozzi's classroom, Epsilon cannot appear within a first set. If something can resolve to epsilon, then it's considered nullable. And this makes some things easier, but the important thing to note is that, for example, here, epsilon would not be in the first set of F. It F would be in the nullable set, and F's first set would currently look like nothing. It would just be an empty set. No epsilon would be inside it. Now, important to note alongside this is that things are ordered. Most things you'll see, well, there's an exception on the very last task. Most things are ordered by the way in which non-terminals appear in the input grammar. So, for example, in the output they give, you'd see A and then B is a non-terminal. It is down here, so B would be next because again, we're going left to right and then up, down. That's kind of a gross looking diagonal. But again, it would be A, and then even though B's down here, next would be B. And even though F's down here, next would be F. C, D, E, F, and that's the ordering. We don't go top down. Most students think it's just top to bottom. It is not. All right. Guidance. So we are given, and in the implementation guide, you guys might see it reference an algorithm that was discussed in class. This one I don't believe was, and the other ones might be modified in ways that would be weird. So here we brought it over. We have the traditional while changed loop where we every time we do something, we set changed and we apply these rules to this rule 2 over and over until we stop seeing change in the nullable set. And this rule is basically saying, hey, if everything within A's rule here is nullable, so if all of these could possibly derive to epsilon, then this left-hand side also can derive to epsilon. And that makes sense because if we have A, B, C, D, all of these are nullable, then it's possible to go, oh, A goes to C, D, which goes to D, which goes to nothing. So A can derive to epsilon as well, and it is nullable. And so we just repeatedly do this rule, and we repeatedly do it because we're constantly adding things to the nullable set. And so we need to check that it's the last thing we're adding. All right. So this is a very common mistake. This is not really specifically relevant to the nullable set. This is more so relevant to every following, basically this and every following thing where you have to look at rules. I see this a lot where a student just implicitly, let's say we have this rule, A goes to B or C. What optimally we'd want is A goes to B, A goes to C, because this or symbol is just a nice way to combine these two together. What actually happens is students, as they're kind of, especially if they use a while loop instead of doing a correct recursive descent parser, is that they continually add this ID list to like a running right-hand side value. So it becomes A, and then they add B, they see or, but they just call parse right-hand side again, and then they add C, or in a while loop, they'll just loop again and then add C. And this is incorrect. This is a singular rule, whereas these two are two different rules. So you might fall into that trap yourself, but just keep in mind if you see a pattern where it looks like, hey, I know there was an or symbol and I'm getting them combined into one big rule, take a look, make sure you're not just adding infinitely and that you're making sure each right-hand side before and after an or is its own rule. So just something to keep in mind and a pattern to look out for as you're debugging. So task 2, the nullable algorithm, as you probably saw, is not really that complex. Try to step through it yourself, work through an example as you've done with first and follow. And I feel most of you can get a grasp on it very quick, especially if you get a good grasp on first and follow. It's just important to note that this is different than what you guys are used to, and that it is really, really, really important to note that epsilon cannot be in your first set in this project. Even though that's what is covered in your class, it's typically what is said in 340 classes, but this is kind of an extended thing that Bozzi started using. All right, Nathan.
Okay. Task 3 is calculating the first sets for each of the non-terminals. So, as Thomas recently just said, do not they do not contain epsilon in this case, and we have the noble set for that and for further calculations. The output in this case is also ordered as they appear in the input grammar. Specifically, the left-hand side from top down is how they're ordered in the input grammar, and each set element is also ordered in which they appear in the input grammar. I've had some students with questioning why their set elements were in the wrong order, and they were looking at like why they were looking more so at how they were added, but in reality, you should how they're added won't match up with the output expected. So you need to sort it at the end after you find all the first set elements. You need to resort it based on how they appear in the input grammar. Okay. And next slide. So if you notice the rules, they're slightly different, and that's because there is no longer any epsilon in the first sets. I believe the original rules there were 5 different rules, and the last 2 were basically the noble set rules. So just to keep that in mind, there's nothing for epsilon in this case for for the rules. Yeah, so there obviously is pseudocode as well. I'm pretty sure that yeah, your teacher did not provide pseudocode. I remember I had a student earlier asking what page this was referencing for the pseudocode because he couldn't find it, but it's because he's using Bozzi's slides, and obviously they're referring to Bozzi's notes. So we will be providing the pseudocode here. So for the algorithm, you have a while loop that basically for every time the first set is changed, you set change equals is true, and you basically keep looping 2 and 3 continuously until the first set doesn't change. Rule 2 is basically looking at the first element, basically the leftmost rule of A, for example, which is B. You add that first of B to first of A. Rule 3 is basically doing the same thing, except it basically as long as all the non-terminals and terminals before B are nullable, you can add that to the first of A. So you continuously loop 2 and 3, and obviously rule 1 you initialize first. One thing I've noticed some students messed up, especially when implementing, was they also had a changed equals false if nothing was changed for a first set. I think I've had 2 students. So I just want to point that out. You you initialize changed equals false at the beginning of the while loop and only do changed equals true. You don't need to do changed equals false because then you have a chance of accidentally canceling out some change that had occurred. So that's something I just wanted to point out in case any of you run into that issue. But you shouldn't. I mean, the pseudocode doesn't say that. So if you follow the pseudocode, you should be fine. Okay. And also for the data structures, almost forgot to mention that. Uh, it's recommended to use an unordered mapping of a non-terminal to a vector, uh, to a set in this case of strings. So basically, you're mapping the non-terminal to the first set, right? So that's also in page 21 of the implementation guide. Sets are fine in this case because the ordering's already messed up in the first place, right? Because the way you add the first elements to the set will not be in the order they're outputted, and the sets will ensure that each element is unique, so that can do that for you. You can still use vectors, but sets are probably a more reliable use case for now in this situation, since you have to reorder at the end either way. Yeah.
I just want to add quick that for those who don't know, an unordered map is a basically behind the scenes a hash map. Um, so it's kind of like a dictionary if you're not too familiar. Um, yeah.
Let's go. And we give this our estimated rating of 2 out of 5. Once again, take these ratings with a grain of salt. This is more so maybe a little metric that might help you. It might not. Just take it with a grain of salt. And obviously, this first sets rely on the noble sets being correct for the algorithm. Okay.
Alrighty, so next up is calculating the follow sets, which now we've got two kind of dependency layers. The follow set relies on the first set being right, which relies on the knowable set being right. Um, and so we calculate the follow set of each non-terminal, and we have a new player here. We have this end of file value. If you ever see this show up in your first sets, something has gone wrong. This should only ever appear in follow sets. And when you're outputting, before we outputted when it showed up in our input, so we went left to right, up, down, kind of in the Z formation. Obviously, this doesn't appear anywhere, so if we're sorting something, and that's another thing is when you're doing an output, I recommend creating a function that you can just pass things into and it'll sort based on the left this kind of Z formation, and it's discussed in the implementation guide. But yeah, so this end of file symbol should appear before everything. Um, so, and then for the rest of it, ordered in the way they appear, they need to be, so the non-terminals are ordered in the way they appeared, then similarly, the terminals that are in the follow set are ordered in the way they appeared. And this is roughly, or this is the kind of output format that your code will be test or output will be compared against. All right. So guidance follow sets are admittedly a little more complex um, than first sets. There's kind of two stages, first and nullable sets. There's two stages here, and we'll discuss them both. This is the raw algorithm, and these are the rules that it refers to, like here, 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 and here. And then you guys should be at least familiar with calculating follow sets, but we'll kind of discuss how this is relevant. Um, so an important thing to note is that we apply rules 4 and 5, and there's no while changed. This might seem weird because if we look here, rules 4 and 5 essentially deal with moving a first set into the follow set of something. So if we are B and we're thinking about what comes after B, well, A1 comes after B. And then we have to ask, okay, what does A1 start with? And so we take the first of this A1 and put it in the B. And then we have to account for cases where something can be nullable because that means if we're deriving it, it's possible that, whoops, it's possible that all of these are epsilon. And the way things end up looking in the derivation is something like this. So we also need to add first here. But the important thing is because we're moving first sets, we're adding a first set to something, we only need to do it once because our first sets are done. The reason we have a while changed loop is because the follow and first sets are constantly changing. Um, we will get through one loop and everything will have changed. So the copies we made are invalid. So we have to redo them until things stop changing. Here, the first set is set in stone. Just loop over every grammar rule and go left to right, copy here. And then if it's epsilon here, it's not epsilon. Okay, now start here. Copy this here, and do copies. The general loop is you do a copy. Is it nullable? If yes, you move forward, do a copy, etc. Now this is the while change loop where we are doing what I like to call floating down. Um, you guys have obviously done this, but if something is at the end, it's possible. So if we had a rule SA and we did the derivation, so we have S, end of file, then we have A, end of file. So the follow of S kind of floats down into the follow of A. And then similarly, if we follow the derivation, we have this alpha B dollar sign. So the follow of A floats down. And then you have to account for epsilon, kind of these all disappearing. But it's kind of that general process of floating down. And here you do a while changed, you apply rules 2 and 3, doing that kind of float. If anything changes, you set it to true, you begin it all over again. Um, if you are confused about things like this and this, try working through it and kind of pretending you're the code yourself and kind of figure out how you're doing things there. The final note I'll say, and I forgot to mention this earlier, when you see this alpha, some students think it's like a terminal or a non-terminal. This alpha essentially translates to anything. So we have no idea what this is. This could be nothing. This could be 600 non-terminals. This could be 500 terminals. We don't care what this is. We're just saying basically dot 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 B. We don't know what came before us, but we're focusing on this right now. And you'll see that a lot in these kind of definitions. All right. Conclusion. As you probably saw, this relies upon your other stuff being correct. Uh, I mean, obviously, at certain points in time, you have to just question the economics and go, okay, I don't know how I'm going to get the 1 point I'm missing on this test case. I'm spending so much time on this. I'm just going to move on. And that's fair, but do keep in mind that in this project especially, things rely on the previous step a lot of the times, less so for the next two. But if your previous stuff isn't working, it's possible that even if your implementation of the follow set is working, you'll lose test cases because of weird calculations. And it's kind of a two-stage thing, whereas first and nullable were both single stage while changed loops. So this is obviously a little more complex. All right.
Okay, now on to left factoring. So what is left factor? So why do we need left factoring in the first place? So if you recall back to maybe during exam one or before, the conditions for predictive parsing, you'll note that there are two rules. The first rules is that all first sets for a specific non-terminal, like given like for multiple rules of a non-terminal, all those first sets of the rules cannot they have to be disjoint in the first place. So that means none of those first sets will contain the same terminals in this case, and that's kind of key here for why we need left factoring. As you can see in the old grammar, we look at t, and since obviously the first of t is going to be the same, like you have e goes to t plus e, and e can derive t. And in both of those two rules, you have the first set of t, which is, the first set of t is not going to be disjoint with itself. So that means we have an issue of left factoring, issue with non-disjoint sets. And that issue is mainly going to cause some issues while creating the parser, if you think about it. If you recall, basically that when you're basically making like the if statement for a parser, like, okay, which path do I go? You use the first sets. And in this case, well, which path do you go? Since the first set of t is going to be the same with itself. You don't know whether to go to t, go to parse t and then call parse e, or just parse t. I think some of you may recall in your previous projects, I don't believe it was with a non-terminal, but specifically term, like there were instances in the previous projects where you would have to peek twice. And we will be using that logic for making the new grammar, I believe, in terms of, so as you can see, you have e goes to t plus e, and e goes to t. So what does that mean? You're going to go to t, right, in both of those cases. So that you're going to just immediately call parse t. Then you create another decision between whether you call e or epsilon, and that new decision will be itself a new rule, in this case e1. Yeah, thank you, Thomas, for the graphics. It's kind of hard to explain it. Yeah, so this is kind of similar to the first project. If you recall, we're having to peek twice, right? So that's the idea. You do two conditional statements essentially to check. So in this case, the pseudocode is provided, and I would highly recommend checking the specs. I think they also give a detailed explanation, but here are some general steps, right? You essentially look at you do a repeat and you go through all of the non-terminals and you basically try to find the longest prefix between any two rules of a certain non-terminal. So if there is a longest common prefix, then you know that there is going to be an issue with left factoring. So you want to get rid of that. So the idea is that you find the longest common prefix. This is not the longest common prefix, meaning the longest string, basically, that is the prefix between at least two rules. So you remove those rules, right? And then you create basically you remove those rules and then you add a rule to the original non-terminal, which is a and alpha going to a new, and the alpha in this case is I guess it's supposed to be alpha. Sorry, the alpha in this case is the longest prefix, and a new being the new rule the new non-terminal you're going to create for this to solve left for left factoring. And that new rule, that new non-terminal you create is going to contain the suffix for all rules in this case. And obviously, if the suffix is epsilon, the suffix will be epsilon in this case, right? And yeah, you add those suffixes to that new rule, and then you create a new set of non-terminals. This is mainly just for keeping track of what things are properly left factored and what don't need left factoring. So you add that new rule, that new non-terminal, a new, to the set of new non-terminals, which I will call the final non-terminals. And if there is no longest common prefix, meaning there is no issue with, non-disjoint first sets, then you can just remove that rule that non-terminal and add it to the new set, because there's no need for left factoring in this non-terminal, because none of them have the same prefix between any rules of that non-terminal. So you keep looping this. Well, yeah, you keep looping this until basically your set of non-terminals is empty. Yeah, you can continue. Unless you have something to explain, Thomas. I didn't really word that correctly. But
No, I mean, admittedly, guys, these last two tests are difficult primarily because it's really these algorithms, especially the way they're kind of laid out, they're very thorough and it's very difficult to grasp them. So really, if you're going to spend your time reading and maybe rereading something and maybe working through an example, it's going to be in these algorithms, especially you'll know this is kind of a general idea, but when you model something, it's sometimes hard to make it into actual code. So you'll see this remove rules with prefix a from R. Keep in mind if R is a vector and you're iterating over R, when you're programming, you almost never want to remove something from a vector that you're iterating over. So really kind of examine that, and as you're translating it to code, I'd recommend kind of doing like a pseudo code, like doing just a comment code as you're writing it, especially if you have trouble like I do, just kind of planning it all out. Because that way, when you run into the problem of, wait, I'm deleting something from a vector I'm iterating over, I have to figure out a solution. You can do that in pseudo code as opposed to your actual code, which will end up looking gross by the time you figure out how to retrofit it. Um, and then you can.
yeah, here's the pseudocode. I don't think your professor provides this, but actually no, this is part of the specs. Never mind. But yeah, I would also highly recommend looking at the implementation guide. I think the last 10 pages are dedicated to just task 5 and like task 6. It's easier to they probably word it in better than I could ever. And they also give a detailed explanation on how to find the longest prefix between two rules. You can go to the next slide, by the way, Thomas. And that gives us our estimated rating at 4 out of 5 stars. This is not as difficult as task 6, but I think the hardest part for people will be just trying to understand what the pseudocode is. So I think, and I would recommend if you're having difficulty with the pseudocode, is just try to understand what left factoring is doing in the first place. That'll make some of the decisions they do in the pseudocode a little easier to grasp, in my opinion. So yeah, obviously understand left factoring before you dissect the pseudocode. Keep track of how you're incrementing the numbers for each new rule, right? As you add a new rule for a certain non-terminal, you increment it only for that non-terminal. Now it's not a global increment, right? So yeah, you can have like A1 and a B1. And as Thomas put, like it's not A1, B2, and A3. And once again, the implementation guide, I think it was like page 20-ish. I actually have it up right now. Yeah, page 23 goes over lexicographic comparison, which can be used for finding the longest common prefix. So I would also recommend looking at the implementation guide if you're wondering how to implement that portion of the pseudocode.
All right, so now we're covering task 6, which is pretty difficult and pretty hard to understand. So this is another one you want to spend some time on if you have it. So first we need to kind of ask, okay, what is left recursion? We're eliminating it, so it'd be nice to at least know what it is. Um, so whenever you see something like this, A to the A, kind of this immediately goes back into itself. That's causes some pretty major problems for our code because we have, okay, parse A. I'm making my beautiful recursive descent parser. This is looking real nice. I'm doing this perfectly. I don't even need a TA. Okay, and then you do this, and now we have an infinite loop because it has no way to tell whether or not it's going to stop. So if you attend, as we mentioned, it's infinitely peaking. We cannot consume any input. This is a pretty major issue. So we have to figure out, is it possible to get rid of it? So this, when I did this project, was pretty difficult for me to understand. So we need to kind of do this transformation. Um, and we'll see how we get from this to this. So, oh, that was weird. It's a colored laser pointer, guys. Wow. Now I don't know how to get my pencil back. All right, there we go. So at some point, probably, we have a rule that doesn't have A going into itself. So we represent that with beta. Basically, some rule where no matter what it is, it could be nothing, it could be an infinite amount of B's. A is not going into itself. It's not calling parse A immediately. But then we have the rules where, okay, it is happening, and we just kind of subdivide them. Then we transform it into this. So you notice each one of these rules now is transformed into this. It has this new A1 tacked on to the end of it. And then we have this new A1 where we have this kind of these values are now appearing on the left-hand side, and A1 is calling itself from the right-hand side. And we also have this epsilon rules. So this confused me at first, primarily because I go, okay, A was on the left, it had this stuff on the right. How is it not? How did it show up on the right? And so what you have to think is, okay, at some point, if we've got A goes to alpha 1, and this goes on forever, at some point, it's going to have to start with one of these betas. It doesn't matter how many times A is called or whatever. It's going to have to start with these betas, and then it'll be followed by all of the alphas that kind of in the parse tree came down to it. So we have A, it'll eventually hit this beta, and then be followed by any number of these alphas. And so this beta will always be first because in order for this to not be infinite, the left-hand side has to eventually hit something. And so we can put whatever this A1 is on the right alongside this epsilon in A1 because it could just be something like this. Then to account for all of these, it's kind of just like okay, we can get alpha 1, alpha 2, and this could all derive from this base A, alpha 3, and that's how this appears on the right side. And it needs this epsilon or else it can't stop. So that's confusing. Hopefully you can look back on this as you're working through it and it can make a little more sense, but try to understand this before you begin. All right. So there's some issues with this though. The algorithm or what's happening is confusing, but the algorithm really isn't too bad. On the previous slide, we just kind of look at all the ones where A is the first thing, chop the A off, make it A1, copy it over, and then add something to all the ones with um, that were the beta rules. So that's weird, but it's not too bad. But there's a problem here. We have an odd case where things can get cyclic. So this A can go to B, which means A could go to B. So we have parse A, which calls parse B, spelt wrong and with something going on there. And then we have, oh my God, he's forgetting everything. Then we have parse B, which calls parse A. So even though these are kind of going to different things, they're bouncing back and forth repeatedly. So this is not an easy thing to solve, and as a result, we're given pseudocode. But we can assume that there is no epsilon and that there's no kind of cycling back and forth. So before we get onto the algorithm, an important thing to note, as you've heard for most of this project, we did this kind of left to right, and we worked on it using that ordering and we outputted it based on that ordering. But you note in the example, and this is in the specs, this A is first, and A is all the way down here. But even then, so D should come second, then B, then C. So A should be way down here. And that's because on test 6, not only are we outputting in this dictionary order, we are doing our operations. The first rule is that we have to sort these based on this dictionary order. And that just simplifies things for us. Um, this is kind of an algorithm that relies on a lot of assumptions. So this is kind of a pseudocode guide. Um, I honestly think you guys should look on this out on your own after kind of reinforcing, or not reinforcing, after trying to convert this on your own. Because this just at a glance is kind of spooky. You just see a bunch of things that are kind of confusing. You see this N and you're like, okay, where did this N come from? Um, and so I guess I'll take this time to kind of show you, give you guys a general indication of how you break these kind of very theoretical algorithms down. And a lot of it is just kind of looking around. So I have no idea what this is looping over. I know I is 1, so that's probably just an index, but I need this N. I don't see an N up here. I don't see it here. I don't see it here. I don't see it here. But I see it here. And so N is the number of non-terminals. So this actually means we are looping over each non-terminal. And this is the kind of thing you want to be doing as you're working through this. So you see J equals I or 1, and it goes till I minus 1. And this I might think of an example. Okay, if I'm on A3, I don't really like that they use A for every non-terminal, but they do. So if I'm on A3, J equals 1, and it goes to right before what I'm currently at. So I'm here. And so I can say this means loop over all previous because I'm grabbing these two essentially. Jay's gonna hit up these two. And so again, here for all R is an element of rules A of I. This can be translated to loop over all of I's rules. And this is, I won't kind of drag this for much longer because, yeah, you can see how it can get a little tedious, but this is what I want you guys to do. Because if we just give you the pseudocode, you guys will be able to maybe copy the pseudocode, maybe even make it into C, and maybe even figure out how to make your vectors and stuff work with it. But you're not really going to understand what's happening. And when you get an error, you're just going to be like, I can't even read the code I wrote because I still don't really know what's happening. So I really recommend reasoning your way. And it's unfortunate, but when you see like pseudocode like this, you need to reason your way through it and kind of look at what each statement is meaning in English. Um, And yeah, important thing to note, he says, "Hey, you're on your own when it comes to immediate left recursion." And again, if we have this kind of removal, you want to be careful if it's something you're iterating over. So if we're removing A of I, or we are removing a rule from I's rules, and we're iterating over it at the same time, that typically causes some issues when we're actually coding it. So usually you want to do a copy into something and just don't avoid that issue. Common issues are that somebody removes something from a list and the iterator thinks it's still going, and then you get a seg fault, and then you're like, how did that even happen? I followed the algorithm. So yeah, big takeaways are just really try and break down this algorithm and translate it. As you can guess, this is pretty hard. The pseudocode is tricky. You have to look over everything. You're having to cross-reference. Even in that first case, we had to look around to figure out what N even meant. Um, so this is not trivial. This is something that takes time. It's not you're not given pseudocode like you might be used to, where it's just raw C, but it doesn't have a semicolon at the end. So this is something that's going to be difficult. But if you put the time in and kind of grapple with it, you'll land at the other side with a kind of really good understanding, and you'll have a really good start. And you can see why sometimes planning is important with some of these because students will just try to copy the pseudocode and suddenly they're cooked. Um, and yeah, so any questions for now? You guys can either talk or you can text or send them in the chat. Oh, there's 4 chat messages. Oh, Nathan answered them. Shout out, Nathan.
Wait, did I answer it correctly? Like, do you have any more confusion on it as well? Just, or do you have a question, Bob? I see you're unmuted.
Hey, I'm Alex.
Oh,
Um, so I had a question about like, can you hear me okay?
yeah, we
Yeah.
can hear you.
Okay. I had a question about, so let's say you have the parser from the first project. Can we use that parser or is this a whole different thing? I'm honestly just like talking out loud here.
It's a new parser. You can't copy and paste it, but the format is the
Okay,
same. It's still a recursive descent parser, right? So it's very
got it.
similar to Project One. You just
Okay.
can't copy and paste it. You know what I mean? Different grammar.
Yeah.
Right.
And actually,
Yeah,
this
so
should
like,
be,
but it's still like you said, recursive descent. What?
it should like the parse functions, the expects, the peaks, all of that is the exact same, but it's just you're doing it on a different grammar. So what you're peaking, and this is a fairly simple grammar. So for example, you'll only have 5 parse functions, maybe 6 if you like you're expecting to file in something different. And so this is a little simpler.
Right.
It's the same process, but different grammar.
And I noticed you didn't go over like anything about like the timeouts.
Oh, yeah, I meant to mention
He
that.
briefly
Uh,
mentions that they're timed.
yeah, if you follow the algorithms that he gives you, um, you should be fine. What usually comes into play is you if you choose a really bad like data structure. If you're doing like quadruple for loops or like crazy stuff, you're gonna time out. Um, and I think in previous semesters you can kind of gauge whether or not you're timing out if you're failing. Usually it shows up in the last two um, parts. You can usually kind of tell if you're missing like two test cases and you have no idea, you don't think anything else is wrong. Try to shave off some times, remove a loop, especially if you're using like a vector over a set and you're finding yourself having to search through that vector a lot. Obviously, if you have to loop through every element, a vector doesn't matter because whether or not you're looping or just finding the element, you have to find each element. But if you're specifically trying to find something and you're looping over a vector a bunch, then consider changing data structures. Or if you're finding yourself
Okay.
three loops deep, it's something to consider because you can if your runtime is like crazy, then you're gonna get timed out.
Okay, so as long as I'm not doing anything crazy, then I should
Yeah,
be fine.
if you follow the
Okay.
like if you somehow translate the pseudocode to a T, you won't hit those issues.
I can
Okay.
answer the next one in the chat.
Uh,
Unless you have another question.
no, I'm good. That was like one of the concerning parts. I was like, what? Because like I saw the algorithms and I'm like, okay. So I gotta follow these. That makes
Yes.
sense. I appreciate it.
Yes.
Yeah. So for representing epsilon in the parser, what it basically is meaning is that ID list can be nothing. So you don't obviously you can't get token or peak epsilon, right? All it represents is the fact that ID list can be nothing. So you just need to take that into account. Uh, I mean, yeah, that's basically it. You technically just you don't
Like
represent it.
using
You just
Well,
basically wait. Go ahead.
it's if you mean like how do you represent it using this kind of vector struct that they recommend, you would just have a vector of strings with nothing in it. Its size would be zero. So like here, if d derives to epsilon, if I'm getting what you're asking, you would represent it with d in this specific implementation, and there would just be nothing inside of this.
I hope one
Or
of
like
us answered your
Nathan's
question.
Yeah, Nathan was asking the or answering how it would be interpreted by the parser, and that's when you see the epsilon in the grammar.
Yeah, I
Let me
think
see
an
if I
ID
can.
list. ID list is like ID list or epsilon. So yeah,
Yeah.
so basically it could just not be ID list. But that's the
Mhm.
idea.
And then we had a slide, yeah, dedicated to what it might look like. So when we post the slides, you can take another look at that. Let me see if I can.
I have one last question.
There you go. All right, what's up?
So going about like Gradescope, where we submit the code, what files are we supposed to submit again?
Anything you modify, basically the rule of thumb is if you added code to it, you submit it. So do not submit the
But
Lexer, do not submit the input buffer. The given files that you shouldn't be touching, you don't want to submit. So if you could make 8 files, as long as they're not the input buffer and the Lexer and they work, you're good.
Okay. Um, and when you're like turning in the files, you said that the tasks build on each other.
Yeah.
Is this the same way labeled as the project one? Like where you have like task one, task two, all nice and neat.
Yeah, so if we look here, you can see how the parsing is kind of a weird one, but for the most part, each section has its own um, point allocation. You
Gosh.
can see the
Okay.
PDF, right?
Oh yeah. Yeah, yeah.
Okay. So yeah,
Oh, that's all the way at the bottom, isn't it? Okay, cool. My bad. All right, thank you.
that's all good. All right. Anything else for now?
No, thank you so much. This is great.
Yeah.
Uh, yeah, I think the algorithms will definitely save our lives here.
Yeah. And then just keep in mind if you have any questions, there are people at the tutoring hour, um, tutoring, sorry, tutoring center, but me, I work from 2:30 to to I'm forgetting my hours. Okay, I work at 12:30 to 2:30 on Tuesday and Thursday, and I work 12:30 to 4:30 on Wednesday. And then what are your hours, Nathan?
Oh yeah, so I work 9 to 1 on Mondays and 9 to 2:30 on Monday and 9 to 1 on Tuesday.
And we're at ECG 104, which is by that like crepe place. Um, and yeah,
Yeah,
this will be posted when my computer is done processing the Zoom footage, which takes a little bit, but yeah, it'll be posted probably within an hour or two.
oh Thomas,
What's up?
bro, the Mariners just got eliminated just now. Are you sad?
No. All right, I'm gonna stop the recording now.